Okay, good morning, everyone. I want to welcome you to another statistical theory class. Of course, today I'm going to walk you through some materials, but for you to be able to understand the connection between what we've done before and what we're going to be doing, I think I need to have a recap on functions. I'm going to say this. Function is very, very important when it comes to probability model and statistical model. Okay, so functions very, very important. So functions, we can have probability function, okay, and non-probability function, okay. So whether probability functions or non-probability function, okay, it involves mapping an input to a particular output. The difference between the two is just like in probability function, when you're using probability function, you are actually assigning figures, you in the range of 0, 1. Okay, you are assigning figures in the range of 0, 1. So if I'm talking about, if I want to know whether my function is probability function, of course, it must obey what I call Kolmogorov axioms. Okay, it must obey Kolmogorov axioms. The Kolmogorov, when I talk about Kolmogorov axioms, okay, I'm actually talking about number one, talking about non-negativity. Okay, non-negativity. Okay, so the non-negativity is actually saying the probability of an event has to be greater or equal to 0. Okay, and 2, normalization. Now, in the normalization, okay, if the random variable under investigation is discrete, okay, we expect the sum of the probability to be equal to 1 if it is continuous. Of course, I showed you yesterday the integral f(s) ds must be equal to 1. But in general, I'm actually going to say the probability of a sample space must be equal to 1. Okay? Then number 3 is additivity. Additivity. Okay, the additivity is actually going to say if A union B is empty, okay, the probability associated with that has to be equal to the addition of the respective probability. It's in general, if I have the probability of EI, where I start from 1 to infinity, okay, it should be the same thing as the probability of EI, I start from 1 to infinity. Okay, so if you take a look at what I have here, okay, these are the axioms, the Kolmogorov axioms. Okay, before I can actually refer to a function as a probability function, it must obey Kolmogorov axioms. Now, let me say this. The probability function gives a mathematical framework of describing, okay, and quantifying uncertainty. Okay, I'm going to say that again. The probability functions provides a mathematical framework of describing, okay, and quantifying uncertainty, okay, and they enable us to study relationship between variables as well. Now, I'm going to say this. Probability function, okay, is very crucial, okay, very, very essential for probability model and statistical model. I'm going to say that again. Probability function, very, very essential, okay, essential for both probability model, okay, essential for both probability model and statistical model. Okay, the probability model uses probability function. Okay, with the probability function, we'll be able to know how frequently occurring is a particular event. And let me say this: the statistical model relies on probability distribution, okay, to actually describe the underlying data generating process. Now, when I say to describe the data, the underlying data generating process, I'm actually going to say statistical. In every statistical model lies probability function and probability distribution. Now, I just talked about probability function, okay? But let me also say this. Non-probability function also have, they are significance in real life. I'm quickly going to talk about the non-probability function as well, because all of these, they are connected to what we're doing. Okay, so I want to talk about non-probability function for 2 minutes. Okay, I mean the non-probability function for 2 minutes. What makes it non-probability function is because it doesn't follow Kolmogorov axioms. We are not assigning figures within 0, 1. Okay, it could be any figure, but how am I going to know it's not a probability function? Is when the Kolmogorov axioms does not hold. When I talk about Kolmogorov axioms, I'm talking about non-negativity, I'm talking about normalization, and I'm talking about additivity. Okay, now I want to focus on non-probability. You can see what I'm doing. I've been having a recap. Non-probability of function. Okay, let me start one of the functions. Let me start with an identity. Identity function. Okay, now when I say an identity function, I'm actually referring to stuff like this. If I have f of x equal to x situation where you return the same value of input for output. That's what we call identity function. Returning the same value of input for output. That's an identity function. And what is irrelevant of identity function? I'm going to say this. Identity function play a significant role in real world. If you want to talk about a medical diagnostics, okay, in medical diagnostics, okay, in medical diagnostics, identity function could refer to as a normal eddy state. Okay, normal. When let me just say this. When if the response, okay, if the response is identity, okay, if the response is identity, so what do we mean? What we mean is that it means we have a normal heady state. Before a patient can before a doctor can treat a patient, the doctor want to put the patient, in an heady state, right? Then the doctor need to have a benchmark. Okay, that very benchmark, okay, identity can be used as that. Okay, where we actually say, oh, the response identity. Okay, for instance, if I take on this patient, okay, and if this very patient is heady, and after treating the patient, it's still going to be heady because the input is going to be the same as the output. It means the patient is not sick in the first place. Okay. Now, I'm also going to say it has a lot of application. Like, for instance, I'm going to give you, in a pipeline software. Let me just say pipeline software. Okay, or neural network. Okay, we normally want to preserve, okay, a particular input. We don't want any change to the input. Okay, so identity function is using a pipeline software where you want to preserve your inputs. You don't want changes to the inputs. I'm going to give you another application of identity function. Okay, it's in regression modeling, and I need you to pay attention. Okay, I need you to pay attention. Okay, at times, maybe I want to look at the relationship. I want to predict wages. I want to predict wages given the years of education. Now I want to use a regression model for that. Has anybody heard about regression model? Okay, so number 3 now. Okay, identity function is used in regression modeling. Okay, in regression, okay, modeling. Okay, in regression modeling, maybe I have stuff like this. Okay, where this guy is years of education. Okay, and this guy is actually wages. Now, situation where I don't need any transformation of the wages. The X here represent the years of education. I don't need transformation for that. I want to believe this is already in a very good statistical standing. No transformation is required. Then it means I'm using identity function. So linear regression, the link function here is an identity, which means we do not, at times you're actually going to see this, right? S squared or square root of x. All of these are transformation. Okay, but identity is trying to say, okay, keep it the way it is. That's fine. Okay, that's what I mean. Okay, I think I just give you identity. Another one that I'm going to talk about, another function. Okay, I've been talking about, if you take a look at this, let me actually call this A, this B, and then this is C. Okay, I'm talking about identity function. Now, I want to talk about constant function. Constant function is very, very useful as a baseline or for reference comparison. Okay, situation where irrespective of the input, okay, maybe f of A equal to Z, f of B also equal to Z, f of C also equal to Z. So what am I talking about? What I'm talking about is whatever values of the inputs, the output remain the same. That's what we mean by constant function. The constant function also has its own significance in the real world. One of the significance of a constant function is a situation where something at equilibrium. where something, a system, maybe a biological system or maybe economy system that has already stabilized. You want to talk about maybe a long-term interest rate that gets stabilized, or a population growth that start leveling up. Okay, of course, this is a typical example of that. Now, I'm going to say another example of a constant function. Okay, for instance, if you talk about non-module, what do I mean by non-module? The non-module is you try to say there is no relationship. Oh, there's no relationship between wage and whatever predator. Okay, then in that regard, you are using a constant function. In that case, here, y is going to be equal to the intercept. That makes sense? Y, the response variable, will be equal to the intercept. The response variable is not related to any predator. Okay, we actually use constant function as a non-module. Okay, what I've just given you now, I've given you a constant function, I've given you identity function. We also have different kinds of function, like quadratic, like cubic, like logarithmic function. There are different kind of functions that we have around, and they are useful, very, very useful. Now, I need you to pay attention. Okay, if I'm actually, in the case of identity function that I mentioned the other time, is you are mapping from X to X. It's an identity. Does that make sense? Okay. Now, what if in a situation where I'm mapping from X to X squared, that become quadratic, okay? Or I'm mapping from X to this, or I'm mapping from this to that, okay? All of this is more or less like a transformation. Okay, these are not identity. Okay, so I just wanted to take note of that. Okay, now I'm quickly going to I'm going to solve a problem now, and I need you to pay attention. Then I'm now going to come to that. I want to solve a problem now, and I need you to pay attention. Okay, now please pay attention. Pay attention. Now, exercise. For each of the following, function, okay, function H, either determine a constant C, such that C dot H, that is a PMF, that is, let me see, that is, let me just put it in, that is the function X such that this is a PMF, or determine it's on now. Okay, thank you. Determine that no such constant exists. Now, I need you to pay attention to this. For each of the following function H, either determine a constant C, okay, C such that C dot H, okay, that is the function, okay, mapping from S to C multiplied by H of S is a PMF. Of course, yesterday we talked about PMF, the probability mass function for discrete random variable, or determine that no such actually exists. Now, I'm going to give you the first question. Okay, on this, the first one. Now, the first one said, the first one, A, okay, the identity function on the set, the identity function on the set, 0, 1, 2, 0, 1, 2, that is number, that is A, identity function of the set. Then another one, identity function, okay, yeah, I mean identity function on this set, identity function on the set, -2, -1, -2, -1, 0, 1, 2, okay. C, constant function, okay, constant function, X, mapping to 1, okay, constant function mapping to 1 on the set, on this set, -2, -1, 0, 1, 2, okay. Now, quadratic function, the function X, another one, okay, the function, okay, X, okay, mapping to S squared on the set, on this set, 0, 1, 2. Please, I need you to pay attention. Okay, what is this actually asking us to do? Now, they wanted to figure out the values of C, that is a constant, in such a way that that guy, okay, we're actually taking set 0, 1, and 2. Okay? Now, and it's an identity function. Now, if I want to solve that guy, okay, if I want to solve that guy, okay, if I really want to investigate whether a PMF, okay, okay, exists, okay, so what I'm actually need to be able to do, I have to investigate for the common god of the common god of axioms. Now, I want to determine the values of C. You know what this guy is trying to say? Please pay attention. Okay, if it's an identity function, A of 0 will be equal to 0. H of 1 will be equal to 1. H of 2 will be equal to 2. Can you see that? Now, I figure out the H. Okay, I figure that how now. Okay. Now, I want to determine what the values of C, okay, it's actually going to be. Now, if I want to determine the values, and I was told that it's a PMF. A PMF is a probability distribution for discrete. Then you know what I need to do. Okay, I need to investigate, I need to, because I want to find the values of C. So what I'm going to do is when I sum, okay, the function together, H multiplied by C, because when you take a look at that, C, H. Now I'm going to have C, okay, H. My H here is 0, plus C, it is 1, plus C, it is what? 2. Then I'm going to equate that to 1. Why am I equating to 1? I'm equating to 1. That's for normalization property on the Kolmogorov axioms. Okay? So if you take a look at what I have now, I'm going to have 3C equal to 1. What is my C equal to? 1 over 3. Is there any question on that? The problem to the first question is actually that. Is there any question on this? Okay. But when you take a look at the second one, please pay attention. Look at the second one. Okay. You actually say that in the second one of the values negative, okay, then we can never have a C. The PMF is not going to be defined for negative. The fact that we have some values that are negative. Okay. Now, if you want to do constant function, okay, for the constant function, okay, for the constant function, h of -2 equal what? 1. All of that is going to be equal 1. That's a constant function. Then you do the same. Whether for s squared, what is going to happen for s squared? H of 0 is going to be 0 squared, 0, right? What is h of 1? That would be 1 squared, right? What is h of 2? That would be 2 squared. So this is 0, 1, 4. That makes sense? You can be given whatever function and ask you to figure out the values of C. Okay, now I want to go into this. Since you understand all of this, I'm going to go into this probability on finding sample space part 2. Now, this is just to walk you through or to refresh your memory on what you've done before. Okay, so in this, I'm going to also go over set theory, fundamentals of set and operation between sets. Now, this is just to tell you different type of set that we have around. Okay, a set could be prime numbers, natural numbers, real numbers, and so on, like that. We could also have empty set, okay, and so on, like that. Okay, now, any question about this? This is just to remind you that, okay, we have different categories of sets. Now, I want to go into set membership, and I need you to pay attention. Okay, we're going to be playing with notation a lot. Please pay attention. Okay, now let me see if this is going to work. Okay, take a look at that guy. That guy is trying to say, if I have a set X, that how am I going to identify whether they are talking about a set or they're talking about a member of a set? That's synonymous with how am I going to identify whether they are talking about this class or somebody in this class. Then if I want to show that this class is big, then I'm going to capitalize. That's why you see I'm capitalizing X. Now, the lowercase x is a member. That is what that guy means. It means X is a member of a set S. Okay? That is what that. And another way to rewrite that, I can say this. Okay? If X is a member of a set X, then the other one is saying, okay, this a set is containing a lowercase s. Just like if I say if I say 2 is less than 5, if I want to write 5 first, I'm going to say 5 is greater than 2. So that is exactly what I'm trying to say. Please, we play with notation a lot. I will advise that you get yourself familiar with notation. Now I'm going to go into an example. Okay. Before going into an example, I also want you to take note of this. This one. Whenever I have this, okay, from, it means it is contained or it is from that. But if I put this, I'm trying to say it is not. Okay, that guy means Y is not a member of that set. Or maybe somebody that's not a member of this class. Now, if I now define my set X, okay, if I define my set X, take a look at my set X. Okay, I'm trying to say S such that it is greater than 3, but less than 4. Now, I can ask someone to figure out what are the members of that particular group. Okay, now I need you to pay attention. Of course, pi is going to be a member. Pi is 3.14 something. 3.14 something is greater than 3, but less than 4. So pi is a member, okay? And of course, 3.5 is also a member, but 5 is not a member. Take a look at that. Was why I said 5, not a member of S. Any question about that? Okay, 5 is not a member. 5 is not included in that particular set. Okay, now, I'm not talking about member anymore, but you know what I want to talk about now? I actually want to talk about, for instance, I have a set. And I have another set C. Okay? If every element in a set A is also a member of a set T, okay? I'm going to give you an example right now. Okay? If everybody that are here right now, you are attending this course, and all of you are also attending another course. Okay? Now, I'm seeing this class as a set S. I'm seeing another class as a set T. Now, then we say S is a subset of T. But let me tell you this. There are two types of subsets that I want to talk about. Please pay attention. I need you to pay attention. Now, when I actually write this, then what that is trying to tell me is this class. T is the University of Minnesota. This class belongs to the University of Minnesota. So this class is a subset of the University of Minnesota. That is what that guy means. Can you see that? That's what it means. Okay? And another way to write that, okay, there's no difference between this and this. The two are the same. Okay? If this class is a subset of University of Minnesota, then University of Minnesota contain this class. That's what I mean. Take a look at that. Okay? Now, another thing I'm going to talk about, please pay attention. Pay attention. We play with notation a lot. Okay? Now, I want to talk about this guy. Okay? Phi it means empty. Okay? If S is this class, before you come to this class, before the first person arrived, who was the first person that arrived here today? Can the person signify? I just want to use it as an example. Who was the first person that arrived this lecture today? Who was the first person? Who was the person when you came to class you didn't meet anybody? Is that can somebody signify? Okay. Now I want to believe the first person that came here today did not meet anybody in class. What the person met was empty. Therefore, empty is a member of this class. Does that make sense? That is what that guy is trying to say. Empty belong. It's a member of this class. Because when you came in, the first person that came in did not meet anybody around. But you know what the person met? Emptiness. That's what it means. Okay? Now, but there's something I want you to see. Okay? Please pay attention. We have proper subset. We have improper subset. Now, I'm going to give you an example of a proper subset. Now, when I say something is proper, okay, when, let's for instance, take a look at this. When S belongs to T, and T does not belong to X, which means T is bigger than S. That's a proper subset. But improper is when situation where S belongs to T and T also belongs to that, automatically they should be of the same size. And that's exactly what we mean here. If you take a look at this, when S and T are not the same, then one is bigger than the other. But the moment they are the same, then it means one belongs to the other one also belongs to the other. That's what it means. Does that make sense? That's what we're trying to say there. Okay, now please pay attention. We're moving, for you to be able to understand this course. We play a lot with notation. You'll be able to see what is, should be able to link that to real life. Now, I want to go into universal set now. Okay? Universal set in mathematics, we're just talking about is synonymous with sample space, collection of possibility. That's exactly what we mean. Now, I needed to pay attention to this. Please look at this. Okay. X is a subset of omega. T is a subset of omega. I'm seeing S as this class. A subset of omega is the University of Minnesota. Then T, another class, also a subset of University of Minnesota. Now, do you understand that now? Okay, now, when you understand that, then we want to go into what we call the power of a set. Now, let me say this. The moment you understand a set, you understand what we call a sample space or the universal set, which is a collection of possible sets that we can have around. Now, the power of a set now is going to talk about what is the possible number of subsets that I can have in a set. I'm going to say that again. The possible number of subsets I can have in a set, and I need you to pay attention. If you want to answer a question that has to do with the power of a set, you need to, four of us, have the understanding of the sample space. Now, take a look at this. You're given a set. How many elements do we have in that set? X, Y, Z. 3 elements, right? Okay. We want to figure out what is the possible number of subsets. If I want to know the possible number of subsets, number one, so mathematically, please pay attention. If you want to answer my question, this is theory of statistics. We advise that you write an appropriate notation. So, for instance, if I want to write the power of a set symbolically, I'm actually going to write this. Can you see that? That one is trying to say power of a set, X. Okay? Now, the power of a set is, I'm going to start with emptiness. Can you see emptiness? I'm going to start when I have X, Y, and Z singly, when they stand alone, when they stand in twos. Okay? Then I'm also going to have the entire sample space. Take a look at that. Can you see that? We have a formula for this. Please pay attention. Now, if I really want to know what is the number of elements I'm actually going to have in the power of a set, then the formula, I'm going to give you the formula right now. Is everyone still hearing me? Okay, make sure you ask question. If an area is not clear, if you don't understand, ask question. Okay, now you know what I will do right now. Okay, the formula is going to be 2 raised to power cardinality of the set. What I mean by cardinality, the number of elements in that set. Now I have S. Okay, X, Y, Z. The cardinality of this particular set is 3. Cardinality, when I say cardinal, okay, the cardinality of a set refers to the number of elements in that particular set. If I want to know the possible number of subset I can have in a set, it's going to be 2 raised to power cardinality of the set under investigation, and that will be 2 raised to power 3. What do I have? 8. Now let us count. If you count right now, empty 1, 2, 3, 4, 5, 6, 7, 8. Can you see that? The possible number is 8. Okay? Now I want to move. To how do we use a diagrammatical way to describe sets. Now what I'm trying to show you right now, if I have an omega, which is universal set, okay, if I have an omega, which is universal set, and I have 2 sets, 2 different sets, one is bigger than the other, of course, the one that is bigger is X, right? So here now, set T is belonging to X. And all of that belonging to the universal set. That's what that guy is talking about. Now, I want to move to another property of set, which we call the complement of a set. Okay, now the complement, like for instance, if I want to talk about the complement of this class, the complement of this class right now are other students in the University of Minnesota that are not in this class. That's what I mean by complement. It's not. Now take a look at that. How do we define the complement? Please pay attention mathematically. Okay, I'm actually going to say X. Like X is like a student from University of Minnesota, but not in this class. That's why you see X, okay, lies in omega, given that X is not a member of S. You see, I understand. Let me tell you this. I understand my statistics. I understand my mathematics because I relate. Okay, I relate all of this to real life examples. When you use a real life example, something that is looking theoretical will be very easy for you to understand. Now, that is a mathematical definition of the complement of a set. Okay, now if you take a look at what I have right now, okay, now this is the diagrammatical representation of the complement, which means I'm not interested in this class. S, unshaded part, is this class. The complement of this class will be the other students or other students in the University of Minnesota that are not in this class right now. That is what you're seeing right now. Can you see that? The unshaded part in this is this class. The shaded part is the rest of the University of Minnesota. So that's what we mean by complement. Okay, now we got some property. Please pay attention. The complement of empty, then is a universal. That's why I say the complement of empty. Okay, if I'm not talking about emptiness, then I'm talking about whole. I'm talking about sample space. And what is the complement of the sample space? The complement of the sample space is going to be empty, so which means the sample space omega and the emptiness alpha, they are mutually exclusive. That's what I mean. Now, then I also want to let you know that if I do the complement of the complement of the complement will return me back to the original set. That is what that guy means, the complement of the complement. Does that make sense? Okay. Now from there, I'm going to talk about relative. Now, I need you to pay attention. There's a connection between relative complement and complement. Please pay attention. When I'm talking about complement, I'm referring to other elements in the sample space that are not in the set that I'm considering. But when I'm talking about relative complement, by relative complement, I'm not referring to sample space, but I'm actually focusing on two different sets. Now, focusing on two different sets, I'm going to say, the element belongs to this set, but does not belong to the other set. Now, take a look at this, and that's why, please pay attention, okay? Take a look at this notation. Oh my God, that notation is saying X belongs to T, but X does not belong to X. Maybe I'm referring to those students who attend this class and who do not attend another class. That's what I mean. That's why I see X lies in T, okay, so that X does not lie in S. And what am I trying to say? Symbolically, then I'm trying to say T minus X. Where is the negative? Where is the negative? The negative is on X, right? If negative is on X, I'm trying to say, the element does not belong to X, but belong to T. Okay, another way I can write that is this notation. We play with a lot of notation. There's no difference between these two notation. Whether I say T minus X or I say T dot X, there's no difference between them. Okay, so that's what we mean by relative complement. Okay, now, of course, I'm giving example. You can see X belongs to T, but does not belong to S. S is unshaded. Can you see S? Can you see the diagram? S is unshaded. Okay, S belongs to T. Okay, if you take a look at what I have here, Okay, I said T minus X, right? Okay, T minus X. So which means I'm not interested in S, element not in S. That's why it is not shaded. The one that is shaded is the one I'm interested in. Now, another property of set is union. You know, I shaded everything here. Union actually means togetherness. Okay, togetherness. I need to pay attention to that. Okay, now you need to revisit the union, the commutativity, S union T, the same thing as T union S, then the associative property hold for union, okay, and so like that. Then I'm not going to go to interception. You've done all of this before, but we need them. The intersection is talking about, I needed to look at the definition here, okay, S intercept T, which is going to read as X, is from S. Okay, X is from S, and S from T. Okay, that is, they have something in common, which is the area that is shaded. Okay, that's an intersection. That's what they have in common. Okay, and we can also have situation where S and T are disjoint. This is situation. There's no connection. They are disjoint. They are disjoint means, okay, they are mutually exclusive. It's either one occur or the other occur. So that's what you are saying. In this situation now, the intersection is empty. Okay? The intersection is actually empty. Okay. Now, we also talk about symmetric difference. Okay, if you want to talk about symmetrical difference, this is what you're going to do. Please pay attention. I want to talk about symmetric difference between S and T. Okay, so if I want to talk about symmetric difference, okay, between S and T, I'm going to find the union of the relative complements of that and that. And we need to first figure this one out. Situation where S belongs to the element belongs to X but does not belong to this one. Then where it belongs to T but does not belong to that, the union, then I'm going to add them up. So that is what we mean by relative, the symmetrical or difference. Okay. Now we have partition of a set. Okay, we have partition of a set. How we can partition set into different parts. Like I have 1, 2, 3, 4, 5, 6. I can do 1, 3, 2. I can do, partition them into different parts. So we can also have that. Then from there, we're going to go into Cartesian products. I think what I'm going to do, I'm going to start from Cartesian products tomorrow. I think I only have this page and this page. So I'm going to merge these two pages with the other page that I'm going to walk you through tomorrow. Okay? So is there any question for me before I go today? Is there any question? Like I said, it looks as if what we're doing now is kind of simple. But the only way you can understand this class for us, understand the basic fundamental, because as time goes on, we're actually going to go more theoretical. But the moment you understand, what we're doing now, it's going to be easy for you. So what I would advise you should do, that's why I'm taking my time. So what I would advise you should do is the moment you're struggling or you don't really understand a particular notation, make sure you reach out. And I want to appreciate those who have been providing me a feedback. Always make sure you provide a rating of your understanding of a class every day. And of course, I'm going to reply you. Like those who send feedback yesterday, I'm replying them today. So make sure, let me know what you're going through, okay? The summer semester is very, very short. This is where I'm actually going to stop today. Is there any question for me before I go? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.